Steam hisses. Pumps hum. Beneath a thick steel lid, glowing blue light ripples through water. This is the heart of a nuclear reactor, one of the most extreme places humans have ever built. But what if, somehow, you fell into it? What would happen second by second? First, it's nearly impossible. Reactor cores are buried beneath meters of shielding, pressurized steel, and layers of security. But let's imagine the impossible. A breach, an open core, and you falling. The first thing that kills you isn't radiation, it's heat. Operating reactors run at temperatures around 300 degrees Celsius and pressures up to 15 megapascals, about 150 times atmospheric pressure. That's enough to flash water into superheated steam that tears through metal. You wouldn't reach the core. You'd be scalded instantly by the coolant. Your body flash-boiled in seconds. If, by some miracle, you pass through that and reach the core, radiation would take over. The neutron and gamma fields inside an operating reactor are intense, billions of times background levels. At those distances, you'd absorb a lethal dose of several sieverts, SV, in less than a second. That's the biological equivalent of being inside the sun's core, only quieter. A nuclear reactor isn't a pit of glowing uranium. It's a carefully engineered machine designed to manage fission safely. At its heart are fuel rods, metal tubes containing uranium or mixed oxide pellets. Between them sits a moderator, often water, which slows neutrons so the chain reaction can continue steadily. Control rods of boron or cadmium slide between the fuel to absorb neutrons and regulate power. Everything sits inside a reactor vessel, surrounded by coolant that carries away heat to spin turbines. Most modern reactors, like pressurized water reactors or boiling water reactors, are sealed systems. You can't see the core directly. Even during maintenance, it's covered by several meters of water, which blocks radiation effectively. So when we say falling into a reactor, we're talking about a purely hypothetical breach, something that design, engineering, and physics make virtually impossible. At the moment of contact, your skin meets water above 100 degrees Celsius, hotter than boiling, but still liquid under pressure. Thermal shock would cause instant third-degree burns. Your body would lose consciousness from pain and heat within seconds. Meanwhile, invisible radiation floods every cell. Neutrons slam into atomic nuclei, ripping apart DNA and generating free radicals that shatter molecular bonds. Gamma rays penetrate deep, delivering thousands of grays, GY, of absorbed energy, far beyond survivable limits. At doses above 8 sieverts, the nervous system begins to fail. Blood vessels leak, organs shut down, and death occurs within minutes to hours. Even workers at Chernobyl, who received around 6 to 16 sieverts, survived only briefly, despite immediate treatment. Radiation isn't one thing. Alpha particles, heavy, stopped by paper, harmless unless inhaled. Beta particles, electrons that penetrate skin a few millimeters. Gamma rays, high-energy photons that pass through your body like X-rays, but far stronger. Neutrons, uncharged, deeply penetrating, most biologically destructive near the core. Exposure is measured in grays, GY, for absorbed energy, and sieverts, SV, for biological effect. A chest X-ray is about 0.0001 sievert. A full-body lethal dose is around 4 to 6 sieverts. The core's environment delivers thousands of sieverts per hour, enough to kill instantly. The good news? You can't actually fall in. Reactor halls are built like fortresses, thick concrete containment domes, steel lids weighing hundreds of tons, radiation monitors, and strict human access controls. Even the fuel pools, where used fuel cools, are shielded under deep water with robotic cranes for handling. Interlocks prevent human proximity when fuel is present. Every barrier, from the steel vessel to the containment dome, is designed to stop exactly this kind of scenario. Nuclear engineers spend decades ensuring no single failure, human or mechanical, can lead to exposure. Even maintenance happens with the core shut down, cooled, and under heavy water shielding. Only one incident in history even remotely resembled this hypothetical: the SL-1 reactor accident in 1961. A control rod was pulled too far, causing a power surge that killed 3 technicians instantly. But even that was not falling in. It was an internal explosion of steam and radiation. Chernobyl's 1986 disaster was another type, a runaway power spike that blew apart the core. At Fukushima in 2011, cooling failure caused fuel melting, not a human falling in. Every accident has reshaped safety: more automation, more shielding, stricter control. What about the blue pools you sometimes see in photos? That eerie glow, the Cherenkov effect, is light from electrons moving faster than light travels in water. It's not open radiation, it's optical beauty, hiding intense physics. If you swam near recently discharged fuel, you'd be safe only at a distance of several meters. Water is an excellent radiation shield, but the closer you get, the more dangerous it becomes. A few centimeters from exposed fuel rods, the dose could exceed 10,000 sieverts per hour, instantly fatal. Thermal burns and radiation injury would occur long before drowning. If the reactor were shut down, decay heat would still reach several megawatts for days, enough to boil water if cooling failed. In truth, you can't fall into a live reactor. Modern nuclear plants are designed to make that impossible. If somehow you did, the combined forces of heat, steam, and radiation would end life almost instantly. The real story isn't horror, it's precision. Every reactor on Earth is a lesson in layers, human, mechanical, and physical, that protect us from our own inventions. When people imagine nuclear power, they often picture destruction. But the truth is, behind every watt of electricity lies one of the safest, most tightly controlled technologies we've ever built. Science gave us the power to split the atom. Engineering gave us the wisdom to keep it contained.